Hi, today we're going to look at graphing an absolute value function. Two of them here, small one, big one. They're both related to each other. So when you see the absolute value, it's going to give us a specific kind of graph. It's going to look like V. Let's see how we get there. Well, table of values, plug numbers in. What numbers do I want to plug in? I just want to plug in small numbers close to the center here. And let's see where this goes. Put a -2 in there. We're going to say y equals absolute value of -2. When you take the absolute value, it's how far away from 0 are you? How far away from 0 is that one number, -2? It's a distance of 2. How far away from 0 is -1? Distance of 1. How far away from 0 is 0? 0. How far away from 0 is the number 1? 1, and then 2. We want to make sure our answers, our y's, start to repeat themselves as we go out. That's going to give us the graph, the shape that we want. And that shape is that V. Now, with this, we have a specific name to this type of problem. In its most basic form, we call it a parent function. Every absolute value graph that we do stems from this. They will all look like this V and maybe be slightly shifted up, down, left, right, and all that. And they might even get skinny and wide or even flip. Let's see what happens when we check this one out. So we can make a table of values. Now, you could plug in any random number that you want to right here, but it's going to take forever because this graph is going to shift. Starting point is to know where do we, what's my center? Where's my vertex? Let's look inside the absolute value and ask ourselves, what's going to turn this to 0? 2. And let's go larger and smaller. And now I want to plug each one of these numbers in and solve. So 3 absolute value 0 minus 2 plus 1, giving us -2. The absolute value, that is 2. Now be careful. This 3 outside is being multiplied to this whole group. I still want it to be multiplied to that answer. 6 plus 1, giving us 7. Let's do that again. Let's put -1 in there, or a positive 1. 1 minus 2 is -1. Absolute value is 1. Multiply that by 3. Add 1. 3 and 1 gives us 4. Do it again. Now we want to plug in 2. 2 minus 2 is 0. Absolute value is 0. Multiply that by that number 3. 0 plus 1, 1. So far, so good. We're just doing order of operations for all this. We're treating this absolute value like it's of the parenthesis that we need. Put a 3 in. 3 minus 2 is 1. Absolute value is 1. Multiplied by that 3. You get 3 plus 1, which is a 4. Now, this is good because our numbers are starting to repeat. Guess what? That last number, going to be a 7. They have to start to repeat themselves. Now, when I plot this, go over 2, up 1, over 1, up 4, 3, 4, 0, 7, 4, 7. All right, so that made it a little quicker. Is there a way to go even faster with this? Yes, there is. The standard form of an absolute value problem looks like this. Okay, what's that gonna do with anything? Parent function, we can use this formula to manipulate this. So this number k at the very end tells us how much our graph goes up and down. In this case, we have a +1. We're shifting our graph upwards one spot. Instead of starting at the origin, like over there, we went up 1. This 2 inside the absolute value tells us how much we're going left or right, and we're moving in opposite directions. That says -2, I want to go 2 to the right, 1, 2. We got that. This 3 out front tells us whether or not we're going to get narrow and skinny or really wide. If it's larger than 1, if it's bigger than 1, our graph gets narrower. So I'm going to take this whole thing and squeeze it together. If this was a number smaller, like a fraction smaller than 1, we end up getting wider. And if I end up having a negative in front of that 3, our graph would end up looking like an upside down V if we had that. further just kind of connections and relationships with everything, that 3 also acts sort of like a slope here. If we start here, we go up 1, 2, 3 over 1, just like when we did linear equations. And that is graphing absolute value functions.